Hello everyone, welcome back to our channel gsipucmysuru. In today's session, we will be starting with the third chapter of our second PUC electronics syllabus, that is Transistor Amplifier. In the last few sessions, we discussed about the fifth chapter of our second PUC electronics syllabus, that is Operational Amplifier, which is called as Op-Amp in short. In that chapter, we saw how op-amp is used as an amplifier. Apart from that, we also saw the applications of op-amp, that is inverting op-amp, non-inverting op-amp, summing amplifier, differentiator, difference amplifier, integrator and so on. So in this particular chapter, that is transistor amplifier, we are going to see how the transistor can be used as an amplifier. So first of all, what is this amplifier? Amplifier is nothing but the process of strengthening the weak signal. So transistor amplifier is nothing but the process of strengthening the weak input signal without the change in the input frequency. That is, if the input signal is like this, the input is a sinusoidal signal whose magnitude is very small. If I am going to give the same input signal for the transistor amplifier, then the output must be like this. That is, this is our output waveform and this one is our input waveform. The output is the amplified version of the input, but the frequency of both the input and the output signals must remain the same. Is there a need for an amplifier? Yes. Almost all of the electronic devices uses this amplifier circuit. If I am going to consider a radio receiver, the signal what is generated with the help of microphone is just few millivolts, and that millivolts has to be converted into volts in order to fill the room with the sound. Similarly, if I am going to consider the musical instrument, the sound signal which is generated with the help of a microphone will be just few microvolts, but that microvolts cannot drive the loudspeakers which is present in the auditorium. So that microvolts has to be converted into the volts in order to fill the auditorium with the sound. Like this, the amplifier circuit is very important in almost all the electronic devices. So transistors anta helidaga, there are two different applications. One is a switch, the other one as an amplifier. So these are the very two main applications of this transistor, but in this chapter we are going to mainly focus on the second application, that is the amplifier. So what is this switch? Whenever I want to use this transistor as a switch, then I have to make sure that the Q point or the quiescent point or the operating point is either present in the cutoff region or in the saturation region. Cutoff region ಅಥವಾ saturation region ನಲ್ಲಿ ನನಗೆ Q point ಇದ್ರೆ, then we are going to tell that the transistor is working as a switch. If I want the transistor to be worked as a off switch, then I am going to make sure that the Q point is in the cutoff region. If our transistor is required to be operated as a switch, that is in the on condition, then we have to make sure that the Q point is selected near the saturation region, because the switch is having only two conditions or the two positions. One is the on switch, the other one is the off switch. So apart from these two regions of a transistor, there is another region what is called as an active region. We have already discussed all three regions of a transistor in the second chapter, that is transistor biasing. Also, we discussed about the quiescent point or the Q point. If I want our transistor to be working as an amplifier, we have to make sure that the Q point is exactly at the center of the active region. Apart from this, there is a need for biasing. If I am not going to bias, that is, if I am not going to connect the external DC source for the transistor will not turn on. So there is very important in order to bias the transistor. So active region ನಲ್ಲಿ ಅಥವಾ if I want that transistor to be working as an amplifier, the emitter to base junction has to be forward biased, emitter base junction has to be forward biased, and the collector base junction has to be reverse biased, and the collector base junction has to be reverse biased. So biasing is very important. So in this chapter we are going to see how the transistor will be working as an amplifier. But selection of Q point is not the only one important parameter. when we want our transistor to be working as an amplifier. We have to make sure that the Q point is not shifting either towards the cutoff region or towards the saturation region. Yake? The Q point must be exactly at the center of the active region. The cutoff region or saturation region kadege hoytu anta helidre, the transistor will no more be working as an amplifier, it will work as a switch. So, maintaining the Q point to be at the same position is very important. Here comes one of the definition what is called as faithful amplification. So what is this faithful amplification? Faithful amplification anta helidre, the process of increasing the strength of the input signal without change in the shape and frequency of the input signal. That is, if I am going to consider an amplifier circuit for which I am going to apply the input signal and output signal will be taken from that amplifier, the faithful amplification ಅಂತ ಹೇಳಿದ್ರೆ, it is the process of increasing the strength of the input signal. This is the input signal what I am giving as input for this amplifier circuit. So as soon as I apply this signal as input for the amplifier circuit, I have to get the amplified version of this input signal, but the shape of the signal must not change. So faithful amplification anta helidre, it is the process of increasing the strength of the input signal without change in the shape of the signal. That is what is called as the faithful amplification. Just now we saw what is the definition for a faithful amplification. For a faithful amplification, there are three condition factors which is very important. The first one is proper zero signal collector current. What is this proper zero signal collector current anta helidre? Collector current is nothing but the output current. Whenever I am not applying any kind of signal at the input side, the collector current must be equal to 0. That is what is the meaning of proper zero signal collector current. When I am not applying any kind of input signal, the output current must be equal to 0. The second one is minimum base emitter voltage VBE. Just now I told you that for a transistor to be working as an amplifier, there is a need for biasing. While biasing, we have to make sure that the minimum amount of base to emitter voltage is always applied between the emitter and the base terminal in order to forward bias that base to emitter junction. And the third case is minimum collector emitter voltage VCE. So these are the different condition factors what is very important in order to get the faithful amplification. That is the process of strengthening the weak input signal without change in its shape is the faithful amplification. Next we are going to see the classifications of amplifiers. These amplifiers are classified in a broad manner depending upon the criteria. There are a number of criteria like input signal, nature of the output, bandwidth, configuration, ಯಾವ configuration, CC configuration, CE configuration, CV configuration, apart from that Q point, ಈ ಥರ ಎಷ್ಟೊಂದು ಬೇರೆ criteriasನಲ್ಲಿ the amplifiers will be classified. So whether it is a voltage amplifier or current amplifier or the power amplifier, and apart from that the frequency range in which it can handle, the amplifiers whatever I am going to design that can be used in order to amplify the signals of certain frequency range. So ಯಾವ frequency range signals ನಾನು amplify ಮಾಡ್ತಾ ಇದ್ದೀನಿ, accordingly we can classify the amplifiers. So the table of this classification of amplifiers is already been displayed on the screen. Please go through that. Let us see how the transistor will work as an amplifier. Concept of working of an amplifier. In order to understand how the transistor will be worked as an amplifier, let us take this circuit. This is a NPN transistor in which the common base configuration is taken. This is the emitter terminal, this is the base and this is the collector. So this is a common base configuration, and the voltage what we are going to apply between the emitter base junction, that is in order to forward bias the emitter base junction, is denoted by VEE, that is nothing but a DC source. Similarly, the voltage source VCB will be connected between the base and the collector junction in order to reverse bias this junction. And even this is a DC source. These are the two sources what we are going to apply in order to give the biasing condition, in order to give the forward biasing condition for this junction and in order to reverse bias this junction. But this is the input signal what we are going to apply between the emitter and the base junction, which has to be amplified. Yava signal na nan amplify madbeko, that signal will be applied across this terminals, that is the base and the emitter terminal. RC is nothing but the resistor through which the output is taken. RC across nalle nanu output voltage na nanu extract martini. So in order to understand this concept of working of an amplifier, as soon as the signal is applied, that is we are going to apply a AC signal. As soon as I apply a AC signal, there is a flow of current what is called as IE. IE alli flow agakke shuru agutte. But since IE current is flowing through the transistor, there is a production of current what is called as the collector current IC. But in the last year itself we saw that IE is equal to IB plus IC. IE is equal to IB plus IC, where IB is nothing but the base current, IC is nothing but the collector current. We also saw that IE will be approximately equal to IC because IB value is very, very small. Hagagi IE will be approximately equal to IC. But that IC is flowing through the resistor RC, whose value will be very, very high usually in an amplifier circuit. As soon as the current starts flowing through this resistor, that is 5 kilo ohm ಅಥವಾ RC ಅಂತನೆ ತಗೊಂಡ್ರೆ RC ಮುಖಾಂತರ IC flow ಆಗಕ್ಕೆ ಶುರು ಆಯಿತು ಅಂತ ಹೇಳಿದ್ರಿಂದ, since this RC value is I, the voltage across this resistor, that is the output voltage, if I am going to denote that by V0, the voltage across that resistor V0 is equal to the current flowing through that resistor IC into the resistance of that resistor. Let me denote it by RC. Even though the value of IC is small, since the value of RC is very, very large, V0 value, that is the output voltage value, will also be very, very high. Let us try to illustrate this numerically. Okay, if the input voltage what I am going to apply between these two terminals is considered as if Vin is equal to 0.1 volts antane tilkolona. The input signal whatever I am applying between the emitter to base junction is just 0.1 volts anta tilkolona. This 0.1 volts help in generating the emitter current. Let me consider that it is around 1 milliamps anta tilkolona. Aita, but since IE and IC values are approximately same, let us consider that IC value is also equal to 1 milliamps. Clear? Now, I want to measure the output voltage across this resistor. IC is nothing but the current which is flowing through that resistor. So, the output voltage V0 will be equal to IC into RC. IC value now is equal to 1 milliamps, 1 into 10 to the power of minus 3 into RC value ಎಷ್ಟಿದೆ. If I am going to consider the same example, 5 kilo ಇದೆ. 5 kilo ಅಂದರೆ 10 to the power of 3. So this gets cancelled. So 5 into 1 which is equal to 5 volts. The input voltage what I applied was just 0.1 volts, but the output voltage what I am getting is 5 volts. That is, the output is the amplified version of the input signal. ಯಾಕೆ ಇದು? Because always the output resistor, that is RC, or the output impedance value will be very, very high. ಹಾಗಾಗಿ whenever I am going to use the transistor, the output will be the amplified version of the input signal. But we have to make sure that this junction is forward bias and this junction is reverse bias. We have to make sure that this VE voltage is at least maintained a minimum value such that this junction is forward bias. Similarly, VCB value must be maintained such a way that the junction is reverse bias. Like this, we are going to use a transistor as an amplifier. Clear? The next topic is general parameters of an amplifier. The different types of BJT amplifiers are designed using any one of the three configurations. That is, there are three different configurations. One is the common collector configuration, common emitter configuration and the common base configuration. Out of these three, we are going to select any one of this configuration in order to use our BJT or the transistor as an amplifier for a specific application based on the characteristics of that particular configurations. In order to select the right amplifier, it is very much necessary to understand the general parameters what is available in a transistor. For that, let us consider a circuit, that is an amplifier circuit, for which the input voltage that is being applied will be denoted by Vin with the input current II, and the output current will be denoted by I0 and the output voltage will be denoted by V0. So there are different parameters or different definitions. Let us look into that definitions one by one. The very first one is voltage gain of an amplifier. Voltage gain of an amplifier will be denoted by AV. A anta helidre it is nothing but gain. AV is nothing but the voltage gain. The voltage gain AV is nothing but the ratio of output voltage to the input voltage. According to this diagram, the output voltage is denoted by V0 and the input voltage, let me denote it by just Vi, the input voltage is denoted by Vi. So, the voltage gain AV will be equal to V0 divided by Vi. Similarly, the second parameter is the current gain, which is denoted by AI. I stands for current. It is nothing but the ratio of output current to the input current. Output current is nothing but I0, input current is II. So, AI will be equal to I0 divided by II. Similarly, the next parameter is power gain, which is nothing but the ratio of output power, that is P0 divided by input power. Right? But the output power, we are having different definitions for this power. Power anta helidaga, it is a product of V into I. P0 is equal to V0 into I0 divided by Pi is equal to Vi into II. That is P0 anta helidre output power, which is a product of output voltage and output current. Pi is nothing but the input power, which is a product of input voltage and the input current. This power gain will be denoted by AP, but V0 by Vi is equal to AV into I0 by II is equal to AI. So, AP is nothing but the product of the voltage gain and the current gain. So, these are the three definitions or the three parameters what we are going to use in our amplifier. There are some other definitions like fourth one, the input impedance, which is denoted by Zi. So, according to Ohm's law, V is equal to I into R. R is equal to V by I. Now I am talking about the input impedance. Impedance is almost equal to the resistance of a circuit. So, Zi will be equal to the input voltage by the input current, Vi by I. Similarly, output impedance, which will be denoted by Z0, is given by output voltage divided by output current. So, these are some of the definitions what we are going to see in the transistor amplifier circuit. There is another one definitions what is called as the bandwidth of an amplifier. The last parameter of our transistor amplifier is bandwidth. In order to understand that bandwidth, we have to consider this frequency response curve. Frequency response curve is nothing but a graph which is plotted between the frequency and the gain of an amplifier. So frequency will be taken in the x-axis and gain will be taken on the y-axis. So this is the frequency response curve, that is, this is the curve what we are going to get after plotting the graph. The maximum value what is attained by the graph will be denoted by AV max, and below the 3 decibels we are going to mark a point what is called as 0.707 AV max, that is 70.7% of that AV max will be plotted. After plotting that line, we are going to get 2 points. From those 2 points we are going to drop 2 vertical lines which will be called as FL and FH, that is lower cutoff frequency and higher cutoff frequency. And the difference between these 2 frequencies itself will be called as the bandwidth. So bandwidth is denoted by BW, which is FH minus FL, that is the difference between the higher cutoff frequency and the lower cutoff frequency. The frequency range which lies between these 2 points is the bandwidth. These FH and FL are called as half power frequencies. Why these two are called as FH and FL as half power frequency anta helidre, the power at these 2 frequencies will be exactly half of that of the maximum power attained. So why we are going to mark this FH and FL below 3 dB decibels or at 0.707 AV max anta helidre, our human ear is not very sensitive hearing device. It is found that if the gain of an amplifier is exactly at 7.707 AV max or the 70.7% of AV max and above that, then the human ear will not be able to identify the changes in the sound signal. Changes in the sound signals ಅಂತ ಹೇಳಿದ್ರೆ ಯಾವುದಾದರೂ ಡಿಸ್ಟೋರ್ಷನ್ಸ್ ಆಯಿತು ಅಂತ ಹೇಳಿದ್ರೆ ಆ ಇಂಟೆನ್ಸಿಟಿ ಆಫ್ ಸೌಂಡನ್ನು ರೆಕಗ್ನೈಸ್ ಮಾಡೋಕ್ಕೆ ಅವರ್ ಹ್ಯೂಮನ್ ಇಯರ್ ಇಸ್ ನಾಟ್ ಕೇಪಬಲ್. ಬಟ್ ಇಫ್ ದ ಗೇನ್ ಆಫ್ ಆಂಪ್ಲಿಫೈಯರ್ ಲೈಸ್ ಬಿಲೋ ದಿಸ್ 0.707 AV max, ಈ ಲೈನಿಂದ ಕೆಳಗಡೆಗೆ ತಗೊಂಡ್ವಿ ಅಂತ ಹೇಳಿದ್ರೆ then our human ear will be able to identify the distortions in the sound signal. That is the main reason why we are going to consider the bandwidth between these 2 frequencies, where these 2 frequencies are plotted with the help of this 0.707 AV max line. A 0.707 AV max line na draw madkondo allinda we are going to mark 2 separate points. One is called as FL, the other one is called as FH, and these 2 are called as half power frequency, or sometimes it is also called as 3 decibels frequency, which will be represented by 3 dB frequency. Yake adanna half power frequencies anta karteve, because the power at these frequencies will be exactly half of the power of the maximum power. Maximum power ಎಷ್ಟು ಇರುತ್ತೋ ಅದರ ಎಕ್ಸಾಕ್ಟ್ ಆಗಿ ಅರ್ಧಕ್ಕೆ ಬರುತ್ತೆ, ಹಾಗಾಗಿ ಇದನ್ನ half power frequencies ಅಂತ ಕರಿತೀವಿ. So 3 decibels gain ಅಂತ ಹೇಳ್ತೀವಿ. The decibel gain, our gain of an amplifier is usually expressed as a number, that is the gain of an amplifier is 20 or it is 50 or 100 anta helteve. But practically we are going to measure the gain in decibels or bells. Bell is a higher value, ಹಾಗಾಗಿ ನಮಗೆ lower values ನ ತಗೊಂಡಾಗ ನಾವು decibels ಅಂತ ತಗೋತೀವಿ. Deci stands for 10. Deci stands for 10. So 1 by 10 bell will be equal to 1 decibel. Practically bell is a larger value, ಹಾಗಾಗಿ ನಾವು decibels value ನ ತಗೊಳ್ತೀವಿ. The power gain of an amplifier in bell will be written as power gain in bell will be equal to log to the base 10 of the gain power, which is equal to log to the base 10 of P naught divided by Pi, where P naught is nothing but the output power and Pi is nothing but the input power. Now the power in decibels will be written as 10 log to the base 10 of P naught divided by Pi, where P naught can be written as V square divided by R. So, power in decibels is equal to 10 log to the base 10 of V naught square divided by R of Vi square divided by R, where V naught is nothing but the output voltage and Vi is nothing but the input voltage. So, this gets cancelled. I will be left with 10 log to the base 10 of V naught by Vi whole square, or 2 into 10 times of log V naught by Vi, that is 20 log to the base 10 of V naught divided by Vi. This is the expression of a voltage gain in decibels, but V naught divided by Vi can be written as power gain in decibels equals 20 log to the base 10 of AV, because V naught by Vi anta helidre AV. Adhe thara in current gain terms anta helidre 20 log to the base 10 of AI. V naught square by R ಜಾಗದಲ್ಲಿ I naught square by into R, ಇಲ್ಲಿ I square into R ಅಂತ ಬರಿತೀವಿ. As usual, R gets cancelled. So, this is all about the power gain of an amplifier in terms of bell and decibel. In terms of bell ಅಂತ ಹೇಳಿದ್ರೆ log to the base 10 of AP, ಅದೇ decibels ಅಲ್ಲಿ ಹೇಳೋದಾದ್ರೆ ಈ ತರ ಬರುತ್ತೆ. The last topic is, what is the need for measurement of gain in decibels? This decibel is nothing but a logarithmic unit, because decibel is equal to ನಾವೇನು ಹೇಳ್ತೀವಿ 10 log to the base 10 of P naught divided by Pi. So, it is a function of logarithmic unit. So, our ear response is also logarithmic in nature. That is, it does not depend upon the intensity of the sound, but it depends upon the logarithmic of the sound. If the sound signal what is generated is increased by 100 log 10 to the base 10 of log 100 to the base 10 of anta bardaga, its value will be equal to 2. That is, even though the gain of an amplifier is increased to 100 times, then our ear will have the doubling effect but not the 100 times effect. So, this is all about some of the parameters of a transistor amplifier. Now, it's time to have a look on part 2 of the session. Hello everyone, welcome back to part 2 of the session. In today's session, we are going to see about another type of amplifier, what is called as the instrumentation amplifier. So, what is this instrumentation amplifier? Many industrial systems, consumer systems and process control systems require a precise measurement of the physical quantities like temperature, pressure, humidity, weight, etc. Say for example, a sugar factory requires a measurement of flow, level and temperature of juice. The plastic furnaces require precise measurement of the temperature. The dairy plant requires a precise measurement of temperature and humidity. The measurement of these physical quantities is generally carried out with the help of a device what is called as transducers. There are a number of transducers available. Some of them are RTD, that is resistance temperature detector, strain gauge or a thermocouple. But most of these transducer outputs are generally of very low level. Such a low level signals are not sufficient to drive the next stage of the system. One more difficulty in the practical system is that the transducer used may be mounted on pieces of the equipment or structures which are remote from control location. So, long connecting wires or cables are required in such a case to get the transducer output to the control room. Due to this, the signal which itself is very low gets subjected to the noise and atmospheric interference. Hence, it is necessary to amplify the level of such signals, rejecting the noise and the interference. The amplifiers must have high common mode rejection ratio, that is CMRR. Hence, a special type of amplifier is used, which is called as the instrumentation amplifier. Instrumentation amplifier uses transducer bridge to amplify the low level signal. This is also called as the resistive transducer bridge. So in this block diagram, the first block is a transducer. After the transducer comes the amplifier, which is called as an instrumentation amplifier. The output of this instrumentation amplifier can be given to the control system or simply a controller. So what is this resistive transistor bridge anta hedadre? It is a device whose resistance varies due to the change in some physical condition. Example, in RTDs, that is resistance temperature detector, resistance changes with temperature. In photoresistors, the resistance changes with change in light intensity. Such a transducer is generally used as one arm of the resistance bridge, and the entire circuit along with the amplifier is called as transducer bridge instrumentation amplifier. So in this we are having a bridge of RA, RB, RC and the resistive transducer, that is RT plus delta R. Delta R is nothing but small change in resistance. If there is any variation in the physical quantity, then that resistance value changes, which in turn changes the output of that particular bridge, which is nothing but a amplifier. With this, let me conclude the part 2 of the session. Thank you. So in this session, we discussed about the basics of a transistor amplifier, that is how a transistor can be used as an amplifier and also the different parameters of a transistor. With this, I am going to conclude this session. In the next session, I will be coming with a new topic. Until then, take care. Bye-bye.